Okay, let's get right into it. When you think brain, you probably picture this. A wrinkly, folded thing tucked inside a skull, right? But what if I told you a brain doesn't have to be in a head? What if it could be, well, everywhere at once? So, right off the bat, let's just throw our usual assumptions out the window. On one side, you've got our brain, centralized, folded inward, looking ahead. But then, you look at the sea urchin. Its brain is spread across its entire body. It's unfolded outward, and it's sensing everything in 360 degrees. It's like a completely alien blueprint for how to be smart. So yeah, that's the big idea we're digging into here. Brains without heads. We're literally going outside the skull to explore a totally different way of thinking about, well, thinking. And this is the question that just kicks everything off, right? If nature has already shown us that you don't need a head to have a complex brain, then what else is possible? It's like we found a clue, so let's follow it, starting with our spiky little friend. Now, you might think the sea urchin is just, a simple creature with a basic nerve net. But nope. Turns out, it's got this stunningly complex system. It's distributed, for sure, but it's also incredibly structured. And what's just wild is how brain-like this whole setup is, even without an actual brain. I mean, we're talking hundreds of different kinds of neurons. It's using the same chemicals, dopamine, serotonin, that are sloshing around in our heads. But there's no CPU, no central command. Instead, it's this beautiful lattice pattern, a nerve ring in the middle, spokes going out to the skin, and get this, that skin is covered in light-sensitive cells. The entire animal is basically one giant, all-seeing eye. Okay, so the sea urchin is piece number one of this puzzle, but to get the full picture, we need to bring in two more big ideas. One comes from biology and the other from the world of network theory. All right, inspiration number two, the chameleon's eye. Now, the researchers didn't just see its optic nerve as a simple wire, they saw it as this flexible, twisty cable. And here's the cool part. The actual shape of that cable, how much it's curved or twisted, can change the signals going through it. It's like a physical filter you can literally tune by moving it around, a mechanically tunable cable. And the third piece is a really cool concept called trauma fields. Now, don't just think of emotional trauma. Think of trauma as any big, strong event that hits a network. A sudden flash of light, a loud noise, whatever. This event sends a pulse shooting through the system. Some of that pulse zips through the short, easy paths and disappears, but some of it gets trapped in these long, complicated loops, bouncing around and around. That reverberation actually leaves a permanent mark, a topological scar. It's like a memory getting physically etched into the network structure. So this is the key takeaway here, this split between fast and slow paths. The fast paths, think of them like a quick reflex. Blink and you miss it. But it's those slow paths where the signal gets caught echoing in those deep loops, that's what creates the memory. It's a really powerful model for how a network can physically remember something important that happened to it. Okay, you ready? Let's put all three pieces together. You take the sea urchin's distributed body brain, you add the chameleon's tunable geometric cable, and you layer on the idea of memory-forming trauma fields. What do you get? You get something totally new and revolutionary, the Urchin origami brain. And this quote from the paper just nails the central idea. The whole point is to build a system where you can change how it thinks, not by tweaking the software or the connections, but by physically changing its shape. You literally reconfigure the hardware to change its mind. The basic building block for this whole concept is called an unfolded brain lattice, or a UBL. And it's basically a direct copy of the sea urchin's design. A network laid out on a frame with that central ring, spokes shooting outwards, and a sensory skin on the outside. But here is where it gets absolutely wild. What if you don't build this UBL on a rigid frame? What if you build it on a flexible sheet that you can fold, like origami? Suddenly, that folding action becomes the master control knob for the entire brain. Let me break down how powerful this is. When the sheet is flat, 2 points on opposite ends are, well, far apart. The signal has a long way to go. But when you fold it up into that urchin shape, suddenly those 2 distant points can be touching. They become neighbors. You've just created brand new shortcuts, totally new feedback loops, all without changing a single connection. By just folding the material, you've completely changed how it processes information. You've switched its cognitive mode. I know, this sounds like something straight out of science fiction.
But the researchers didn't just stop at the theory. They actually laid out a roadmap for how you could build one of these things. This is a serious engineering proposal.
And they're looking at two different ways to do it. The first is the wetware path. That means actually growing living neurons, brain organoids, on a 3D printed scaffold shaped like an urchin. The second is the hardware path, building a flexible computer chip, maybe with things like memristors, that you can physically fold like a piece of paper. And again, this isn't just hand-waving. They have actual target specifications. For the wetware version, they're talking about a structure just 5 millimeters wide, with maybe a dozen spokes, but packed with up to 1 million neurons. They even thought about the timing, the communication speeds, aiming for a range from a super fast 10 milliseconds all the way up to a full second. Why? To capture both those lightning-fast reflexes and those slow, echoing loops that form memories.
Okay, let's step back for a second and just think about how big this is. I mean, what does it actually mean if you can physically fold your thoughts?
The big idea, the one to really let sink in, is this: cognition by reconfiguration. The act of thinking itself isn't just electrical signals. It could be a physical process of reshaping, of changing the geometry of your own brain to tackle a new problem or even shift into a different state of mind. And why does this matter? Well, for starters, it completely demolishes the idea that brains have to be stuck in a head. It suggests that geometry itself isn't just the box the computer comes in. The geometry is the computation. This could lead to totally new kinds of resilient AI or smart materials that can change their properties on the fly. And it gives us a whole new way to think about things like memory, learning, and even trauma. So we kind of end up back where we started, but the question is so much bigger now. It's one thing to know that nature has different designs for brains, but what happens when we can build systems where changing the physical shape literally changes the thought? What does that mean for the future of intelligence itself? Not just for AI, but for us.